When did you get here? Didn't notice you were there. I was just starting my Monday morning off with a little bit of jazz and some morning coffee. Actually, there's nothing in here. Anyway, you're here to learn about spontaneity and free energy. So let's get right to it. Spontaneity and free energy. So we've been spending the last few classes talking about entropy and how we need to evaluate the entropy of the universe if we're going to understand whether or not something is spontaneous. Well, what we're going to try to do in this short lesson is give you an idea as to how spontaneity is actually connected to the concept of free energy. So let's get our title out of the way and let's come back to this equation here. Do you recognize this equation? You better. It's the second law of thermodynamics, or at least it's related to the second law of thermodynamics. Namely, here we have the change in the entropy of the universe is equal to the change for the system plus surroundings. And what we know from the second law is that in order for a process to be spontaneous, the change in the entropy of the universe must be positive. Okay? The entropy of the universe must be going up. Now, what we've learned in the last few videos is how to calculate some of these entropy changes. For example, we've come up with a number of different ways of calculating the entropy change for the system. We talked about doing products minus reactants. We know how to calculate the entropy change for expanding or compressing or heating or cooling an ideal gas. And we've also come up with a way of evaluating the entropy change for the surroundings that was based on heat change divided by temperature. There was a minus sign in there and all of that stuff. So when we combine these two ideas, we could eventually get to the entropy change for the universe. But it turns out it's not quite as simple as that, because whenever something happens, there's a lot that's going on. And so we may never successfully get a hold of all of the heat exchange, or we may not be able to account for everything that's going on in the system. So it turns out trying to apply this equation here and evaluate the entropy change for the universe can be a little challenging. So what we're going to do in this video is come up with sort of a derivation, if you will, of how to get the entropy change for the universe by way of free energy. Now, in order to do that, I'm going to need to erase a couple of things here. Let me get rid of my little arrow signs, because I'm going to play around with this equation. So I'm going to slide it up the top there. So starting with this equation, I'm going to do a few simple little bits of algebra. The first thing I'm going to do is I'm going to plug in our substitution that we have for the delta S of surroundings. So the entropy change for the universe is equal to the entropy change for the system minus delta H divided by T. Okay, remember, that's the relationship we kind of came up with a couple of videos ago about the entropy change for the surroundings. Now I'm going to go ahead and I'm going to multiply both sides by negative T. So this now becomes negative T delta S of the universe is equal to negative T delta S of the system plus delta H. Okay, just multiplying both sides by negative T. Now I'm going to introduce a new term here. And the term I'm going to introduce, I'm just going to make a little bit more space for myself. The term I'm going to introduce is this. I'm going to define a new function, and that function is going to be called delta G, and that is going to be equal to negative T delta S of the universe. Okay, so I'm just introducing this free energy concept. Okay, free energy really is the change in the entropy of the universe at a specific temperature. So now I can rewrite that previous line, and let's do this in red because it's kind of a big moment. We're going to have delta G is going to be equal to, and I'm just going to rearrange the terms here to put it into the conventional order, delta H minus T delta S. You'll notice I've also dropped the subscripts because everything's going to be referring to the system. If I don't include subscripts, because we're chemists and we care about the system, the object of study, then I'm implying the system. So I'm going to go ahead and box, star, and smiley face this equation because it's a biggie. Take a look at what we've done here. I can evaluate the free energy change of a process if I know the enthalpy change for that process okay, the delta H, and we've got a whole bunch of different ways of calculating delta H. And if I know the entropy change, or excuse me, the entropy change of the system at a specific temperature. And delta G is a function of the entropy change of the universe. So I'm getting information about the universe merely by evaluating the heat exchange of the system and the entropy change of the system. Now, this is important because this is going to allow us to do a little bit more work. One of the things it's going to allow us to do is evaluate spontaneity. Remember, according to the second law of thermodynamics, something is spontaneous if, during its happening, the delta S of the universe goes up. It's positive. Well, you can see from this relationship right here that if the delta S of the universe is positive, then the delta G is negative. So I now have some new relationships here. A process will be spontaneous if the delta G is negative. That's how I get a spontaneous process. Okay? So kind of a big moment there, really key idea. Now let's see if we can actually expand on this and come up with some other important features here. So what I'm going to do is I'm just going to kind of move some stuff out of the way for now. See if I can get all this out of my way. And I'm going to consider the case of water. Okay? Now, here's water melting. Now, we all know water melts under certain conditions. So then what must be true about the sign of delta G? Well, let's consider those certain conditions. How about if I were at some temperature at T greater than 0 degrees Celsius? At T greater than 0 degrees Celsius, if I looked at water going from solid to liquid, what must the sign of delta G be at T greater than 0? Well, this process happens at temperatures greater than 0, so delta G itself must be less than 0. That would tell us that it's spontaneous. How about at a temperature less than 0 degrees? Well, we know that ice does not melt at temperatures less than 0 degrees, so then the delta G here would be greater than 0. Now there's one temperature that's going to be a special case for this particular reaction. What's that one temperature? What was that? Did you say 0? You're right. Okay. So at temperature equal to 0 degrees, what's going to be the value for delta G? It's negative at T greater than 0. It's positive at T less than 0. So what do you think it's going to be at 0? That's right. Delta G is going to be equal to 0 at, for this reaction, temperature equals to 0 degrees Celsius. So what does that mean? Well, it's spontaneous at temperatures greater than 0. It's non-spontaneous at temperatures less than 0. So at temperature equal to 0, and the delta G is equal to 0, what is that condition? It's a very peculiar condition for this particular reaction. I'm going to write it out here, and yes, it's equilibrium. When the delta G is equal to 0, that system is at equilibrium. So we have here kind of the thermodynamicist definition of equilibrium. You've kind of learned the kinetic definition of equilibrium, when a reaction is equally fast going this way as it is going that way, right? But now we have the thermodynamicist definition of equilibrium, and that is when the system has a free energy equal to 0. What does that mean when the free energy change is equal to 0? Well, if we go back to some of our previous ideas, if I can get this stuff back here, right? If the delta G is equal to 0, if this guy's equal to 0, then what does that mean about the delta S of the universe? It too must be equal to 0. So in other words, nothing's changing in the universe if you are at equilibrium. That kind of makes sense, right? There's no net change to the universe when you're at equilibrium. So here's what we did. We talked about spontaneity and free energy. We introduced free energy as being a concept that's related to the entropy change of the universe, and we've articulated how the free energy change has specific values for specific reactions under specific conditions, which led us into the thermodynamicist definition of equilibrium. Some pretty heady stuff here, so you might want to watch this video again and pause it and take really good notes. That's all for now.